Hi, I am Vansh, and today I am going to talk about Hack CPU design and its implementation in HDL code. So basically, it consists of three input pin as instruction, which is from instruction memory, input M, which is from data memory, and 1 bit reset pin. We are also having four input pin as out M, which tell us that which output we want to write in the data memory. Write M tell whether to write or not in that memory, and address M tell the location or address where to write in data memory, and program counter hold the address of next instruction. It consists of parts like multiplexer, A register, D register, ALU, and program counter. Now the implementation of HDL code is following. Here we declare the chip name as CPU. Here we are having all the input as input M, which is the input from the data memory, instruction, which is the input from the instruction memory, that is A instruction or C instruction, and reset is the signal whether to restart the program or not. It is single bit input. We are having these at output pin. Out time tells what to write in the memory, that is data memory, and write time tell whether to write or not into the memory, and address tell the location or the address where we want to write in the memory, and program counter hold the address of next instruction. Here we are having a basic logic gate as part and all the register, ALU, and program counter. Here we are using not get, in which as input we send the first bit from the instruction, which is indexed at 15 from the right in the first. It is the opcode. If it was 0, then the output is 1, that it was a instruction. If it was 1, then the output for instruction is 0, that means it was the instruction. And here we are sending the instruction as input. If it was not an instruction, then this output is 0, and output for the instruction become 1. Now here we are using AND gate and checking that it is an C instruction, and also the destination for it was the A register. Like if it was C instruction and in destination bit A register bit is equal to 1, then enable to write in the A register, that is ALU output is fed into the A register. Now here in the mux 16, A pin is set equal to the instruction, it is the A instruction, and B is set to the ALU output, and selection is set equal to the ALU to A, and output is equal to A register. It will basically select that fed A instruction or ALU output into the mux 16 on the basis of this selection pin. Now here we are checking that either it was the ALU to A output or either it was the A instruction. Then enable the pin for A register, that is loaded, to load this value. Now A register take input as A register in, which is output for this multiplexer, and load is set equal to load A, which is from this OR gate output, and output of this register is equal to the A output. Basically here we are sending the value of either A register or ALU output, either A instruction or ALU output into the A register. Now here we are using an multiplexer again. Here we are taking output from the A register and the input from the data memory, and load pin, the selection is set equal to the first bit from the 7-bit control bit instruction, which is indexed at 12 from the right hand side in the bus, and it will output either A register value or either input from the memory. Now here we are using AND gate, in which we are checking that it was C instruction and also its destination bit, that is destination 3 bits, in which D bit is 1. Then it will load its value in D register and enable its load. Now here we are using D register. We are sending here ALU output as input and load pin equal to load D from the AND gate output, and out of D register is D out. Now here we are using ALU, hack ALU, in which as input we are sending one input as D register output and one is either A register output or input from the data memory. Here ZX, NX, ZY, NY, F and NO all are set equal to the 6-bit control bit instruction on the basis of which ALU performs certain operation and store its output into the ALU out. And here ZR and NG are two other output which tell if either the output was 0 or negative. If ZR is 1, ZR output is 1, then the output ALU output is 0. If NG is 1, then the ALU output is negative. Here we are using OR16 to set the address of the data memory, in which as A we are sending 16-bit 000 value, 16-bit 0 and 16-bit A register output which store as a 15-bit address to select in a data memory. Here now again we are using OR16 in which we again send A input as 16-bit 0 and B equal to ALU output, which basically set the output for the data memory. And here we are using AND gate for checking that it was C instruction, and also destination for the data memory is 1. Destination is data memory and its load pin was 1, which is indexed at 3 from the right hand side in the bus, and it will output as write M, whether to write or not in the memory. Here we are using AND gate in which we are passing ZR output and instruction bit which is at index 1. It is from the 3-bit jump instruction. It will check that ZR output, that is ZR pin is 1, means ALU output is 0. Also jump pin which is indexed at 1 is 1, then it will output the jump equal to condition equal to 1, jump if equal to 0 condition. Now again we are using AND gate, taking A input as NG out, it means that ALU output is negative, and taking first bit of the 3-bit jump instruction which is indexed at 2 from the right hand side in the bus, and it will enable the output equal to jump if less than to 0 equal to 1, means it make output equal to 1, that is jump if less than equal to 0 equal to 1 when we are having NG out equal to 1 and this bit equal to 1. This is basically from 3-bit jump bit. Now here we are using an OR gate in which we are using a ZR output as A input and NG output as B input. If either it was negative or it was 0, so it make the output ZR or negative equal to 1. Now here we are using NOT gate in which input we send the output from the OR gate, that is either it was 0 or negative, and output of this NOT gate is positive. It means if neither it was 0 or nor negative, then it must be positive, and vice versa. Here we are using AND gate, if and sending A input equal to positive and B equal to instruction at index 0, which is the last bit of the 3-bit jump instruction, index as 0 from right in the bus. It enable the output equal to 1 for jump if greater than equal to 0, which means if the output was positive, then jump if greater than equal to 0 condition become true and output become 1. Here we are checking that A input is equal to jump if equal to and B is equal to jump if less than 2, then either it was equal to or it was less than, then it make the condition jump if less than equal to 0 true, and this output become 1. Here we are using again OR gate, that checking either it was jump if less than 2 or it was jump if greater than, whether we have to jump to A register value. Now it is 1 when either of this condition was true. Here we are using AND gate in which we are sending A input equal to C instruction, that it was C. We are checking that it was C instruction and also jump to A, that is jump condition was true, then make the PC load output equal to 1. Now here we are using NOT gate, if the PC load output is not equal to 1, that is neither it was C instruction nor it was that is it may be no C instruction and maybe jump condition not true, then it make PC load equal to 0. Now and there we are checking that if PC load is equal to 0, then increment the PC and make this PC increment pin equal to 1, that is this not get output equal to 1. Here we are using that is program counter chip, in which in input we sending a register output, increment equal to PC increment load pin equal to PC load, reset pin equal to reset. It will check it that reset pin is equal to 1, then it will restart the whole program. Then it will check if the load pin equal to 1, then it will load the A register output as the address of next instruction. Otherwise it will increment the next instruction address and store the next instruction address in this output. That's the okay.